Ever stop and wonder how your computer can juggle a dozen different things at once without completely falling apart? It's all about keeping order, like a digital traffic cop. And to really get it, you first have to throw out one of the most basic rules of math you've ever learned.
Seriously, think about that for a second. It's just fundamental, right? It's arithmetic 101. But what if I told you that deep inside your computer, that simple, reliable equation can go spectacularly wrong?
Yeah, you heard that right. Sometimes the answer is 0. Sometimes it's 2. This craziness happens when different parts of a program try to change the exact same piece of information at the exact same time. The result? Total chaos. To see how, we're going to need to put on our detective hats and investigate a digital crime scene.
So here's the scene. We have a shared number, a counter, and it starts at 5. And we have 2 suspects, or processes. One is a producer, whose only job is to add 1 to the counter. The other is a consumer, who subtracts 1. Now, if you do 1 addition and 1 subtraction, you should end up right back where you started, at 5. But let's see what happens when they get their wires crossed.
Okay, watch closely. This is where the heist goes down. At the start, both the producer and the consumer read the counter's value. They both see the number 5. The producer thinks, okay, 5 plus 1 is 6, and gets ready to save that result. But wait, before it can, the consumer, who also started with 5, thinks 5 minus 1 is 4, and it quickly saves its result. Then, a split second later, the producer finally saves its value of 6, but it's immediately overwritten by the consumer's value of 4. The final count is 4, not 5. Our data has been corrupted. The crime is complete.
So what do we call this kind of digital felony, this wild situation where the final answer depends entirely on the unpredictable timing of who gets there first? Well, it's got a name. It's officially called a race condition. It's when a bunch of processes are all trying to mess with the same piece of data at once, and the final result is just a total crapshoot based on the exact, chaotic order they execute their instructions in. The name is perfect, right? It's literally a race. Think of it like you and a friend trying to edit the exact same word in a Google Doc at the exact same nanosecond. If you don't coordinate, the final sentence is going to be a jumbled mess. That's a race condition. So, now that we've identified our culprit, we need to secure the crime scene. All right, knowing the problem is one thing, but now we have to define exactly where the crime happens and lay down some ground rules to stop it from happening again. That specific part of the code, that little danger zone where our shared counter is being read and changed, has a special name, the critical section. You can think of it as the room where the safe is. It's the one place we absolutely have to protect. And that leads us to the million-dollar question in computer science. How in the world do we build a system, a set of rules, that guarantees only one process can be in that danger zone, in that critical section, at any given moment? It turns out any solution that works has to follow 3 non-negotiable rules. First, mutual exclusion. It's a fancy term for a simple idea. 1 at a time, please. If someone's in the critical section, everyone else has to wait outside. Second, progress. This means if the room is empty and someone wants to go in, you can't just leave them waiting in the hallway forever. You have to let someone proceed. And third, bounded waiting. This rule is about fairness. You can't let one process get stuck waiting while a bunch of others keep cutting in line. There has to be a limit. So, to enforce these rules, we're going to need some tools. Let's open up the Digital Detectives Toolkit and see what we've got to prevent these data crimes and restore order. 2 of the most famous tools in the shed are mutex locks and semaphores. A mutex lock is pretty simple. Think of it like the key to a single-person bathroom. Only one process can have the key, or hold the lock, at a time. If you have the key, you go in. If you don't, you wait. A semaphore, on the other hand, is more like a bouncer at a popular club that has a strict capacity. The bouncer keeps account of how many people are inside and only lets new people in if there's room. Putting them side by side makes the difference crystal clear. A mutex is a simple on or off switch, locked or unlocked. It's perfect for protecting one single critical section. A semaphore is a counter. It can count from 0 up to some number, which makes it perfect for managing a pool of resources. Like say you have 5 available database connections and you want to make sure no more than 5 processes try to use them at once. But, and there's always a but, what happens when the very tools we use to create order end up causing a whole new kind of chaos? This is the final mind-bending twist in our story. So we've brought in these locks and keys to stop processes from crashing into each other, but by doing that, we've accidentally created a brand new and honestly even scarier possibility, a complete and total system standstill. Let's walk through this recipe for disaster.
Imagine process 0 grabs the key for lock S. At the exact same time, process 1 grabs the key for lock Q. Now, here's the problem. To finish its job, process 0 needs lock Q, but process 1 has it. And to finish its job, process 1 needs lock S, which process 0 has. They are now stuck in a digital standoff, each waiting for the other to give up a key that they never will. This is a deadlock. Nothing moves. Ever.
And if you think this is just some nerdy computer science puzzle, think again. This exact problem brought a multi-million-dollar mission to a screeching halt on the surface of Mars.
The Mars Pathfinder rover, Sojourner, had just landed. It was a huge success. But then, it started just randomly rebooting, over and over. The brilliant engineers at NASA were baffled. It wasn't a broken wire or a faulty part. It was a ghost in the machine, a subtle bug in the synchronization software.
The culprit had a name: priority inversion. Here's what was happening. A super important, high-priority task needed a resource, but that resource was currently held by a little, low-priority task. Now, normally, the little task would finish up quickly and release it, but before it could, a medium-priority task would jump in and interrupt it. So you had the most important job on the rover stuck, waiting for the least important job, which was being blocked by a job in the middle. The whole system's priorities were turned upside down, and eventually a watchdog timer would just give up and reset everything. The fix was absolutely brilliant. The engineers back on Earth figured out how to remotely turn on a feature called priority inheritance. Basically, if a high-priority task needed a lock held by a low-priority task, the system would temporarily boost the low-priority task's importance to be just as high. This meant the medium-priority tasks couldn't cut in line anymore. The little task could finally finish its job, release the lock, and let the whole system get back to work. All fixed with a software patch from millions of miles away. Incredible. And that story really captures the fundamental battle here. The tools that prevent chaos can accidentally create total gridlock. This leaves us with the single biggest challenge for the future of computing. As we build machines with hundreds, maybe thousands of cores all running in parallel, how do we design systems that are perfectly safe from data corruption, but also fluid and fast enough to avoid getting stuck in a deadlock? That right there is the true art of digital order.